In this video, we're going to go over the paper called Neural Manifold Clustering and Embedding, the preprint of which is available on arXiv, and which to me it seems to be a pretty interesting article. The first thing we want to talk about is manifold clustering or nonlinear subspace clustering. The aim of this is to cluster the data points based on these manifolds and their structures, and then parameterize these manifolds as a linear subspace in a semantic space or in a feature space. Neural networks seem to be a perfect fit for this problem because of the high capacity that they offer and due to their flexibility. The authors mentioned that in order for this to be achieved by neural network, two key ingredients are needed. One of them is a learning algorithm with the objective of parameterizing these manifolds and representing them as a linear subspace in a semantic space. And the other one is a domain-specific constraint that ensures that the manifolds can be correctly identified. We will see throughout this paper that the authors show that augmentation, which is a traditional tool that is extensively used in the machine learning domain, is good enough to help us implement these constraints in practice. As a note, the focus of this paper is on these two ingredients, and for the learning algorithm, the key point to discuss is MCR2, or maximum coding rate reduction objective, and for the constraint, the focus is on data augmentation, which ensures that these domain-specific constraints can be satisfied. Putting these together, this paper proposes the NMCE method, or neural manifold clustering and embedding, with the objective of outperforming the state-of-the-art in this domain, which are basically mostly autoencoder-based techniques. They also a little bit investigate the relationship between the neural manifold clustering and embedding and the famous self-supervised learning objectives and techniques. The focus of this paper is on the problem of unsupervised representation learning, which its definition is here, to learn features from data without the use of any labels. In case the data lies in a linear subspace, which is perhaps the simplest form of this problem, this linear subspace can be extracted via PCA. In the relatively more complicated case in which we have to deal with a union of several linear subspaces, the SC or subspace clustering algorithm is going to be needed. It is needed to perform the task of manifold clustering, meaning to cluster each data point, as well as basically parameterizing each one of these manifolds. Now, the problem in this article is the more challenging scenario in which we have to deal with a union of several nonlinear and low-dimensional manifolds. Thus, the problem can be reformulated this way. The input of the problem are data points that come from a union of low-dimensional manifolds. The output is basically segmenting these data points based on the corresponding manifolds and also obtaining a low-dimensional embedding representing each one of these manifolds in a semantic space. The introduction mentions that even though a lot of methods have been proposed, it is still an open question as to how to effectively use deep neural networks for this purpose. The method proposed in this article is called neural manifold clustering and embedding, and it follows three main principles. The first one is, in order to make sure that manifolds are identified properly, and we will see some examples of that, there has to be a domain-specific constraint. An example of this domain-specific constraint is a preservation of local neighborhoods, local linear interpolation, or data augmentation invariance. Roughly speaking, this is very similar to the self-supervised learning principles, meaning that data augmentation and the small perturbations should not change the representation in the semantic space too much. The second principle is that these manifold representations shall not collapse. And the third one is that these manifolds that are identified and parameterized should occupy different linear subspaces. In the article, to achieve one, data augmentation is used, and the MCR2 algorithm is mostly used as an objective to achieve 2 and 3. Thus, the main contributions are combining the data augmentation with MCR2 and exploring the connections between this algorithm and the self-supervised contrastive learning, and also showing that empirical validation indicates that NMCE achieves a strong performance. And on more challenging tasks, mainly image recognition tasks of Cipher 10 and Cipher 20, it can outperform the best algorithms that are currently available. ensuring that the feature space or the semantic space that this algorithm learns is meaningful and interpretable. Let's go over the related work section. The first thing mentioned here is the classical manifold learning. The objective in there was to map the manifold structured data points to a low-dimensional representation space in a way that the manifold structure is preserved. So there are two key ingredients in this. One is that we want to make sure that the embeddings should not collapse to a trivial solution, which means that the variance of the embedding space must be maintained somehow, usually by basically modifying the objective. And the other one, choosing a geometric property from the original data space to be preserved. For example, in approaches such as the word to vec, the idea was that king minus queen, if we have the representation of king minus representation of queen, be similar to this, which is an example of constraining the manifold in the feature space or in the semantic space in a way that some geometric properties from the original data space, which we expected, are maintained. Now, manifold clustering is needed when the data has to be modeled as a union of several manifolds. When these are linear, the subspace clustering SC algorithm can be used, but the focus here is mainly on the nonlinear case, which is more general and more challenging. The authors mentioned that the past work in this domain mainly lie into three categories. Locality preserving is the first one of them. In the locality preserving techniques, there is this implicit assumption that manifolds are smooth and that they are sampled densely. The method proposed in this article, meaning NMCE, achieves this by basically geometrical constraints. The second are kernel-based techniques, in which the suitability of the underlying kernels are important. And it often needs the data to be represented in a space that is a lot more high-dimensional than the data space itself. And in the neural network-based domain, which is the third one, there are some deep subspace clustering methods that have been proposed, which focus on jointly performing the linear subspace clustering, task 1, and representation learning. The main drawback of this is that it is shown that most of the gains in performance have been obtained by the ad hoc post-processing techniques that have been used in these works, and that the use of neural networks wasn't the key component in improving the performance of these works, as it just provided minor improvements over the use of linear subspace clustering algorithms. Now, there are some points in which this work is different from the others. The first point is that as most of the proposed works in this domain rely on autoencoders and GANs, meaning that they are generative models, this work is a contrastive method. The other point is that the previous methods use self-expression based subspace clustering. Here, the MCR2 objective is used for that. And the third one is that while many of these works use data augmentation as a complementary step, in here, data augmentation has a central role, allowing the identification of these manifolds. In the self-supervised learning domain also, similar to the problem of manifold clustering and embedding, which is the focus of this paper, there are two main ingredients. First is the use of data augmentation to enforce domain-specific invariance, and the second one is the fact that the latent representations should not collapse. Some of the more recent works propose feature orthogonalization and decorrelation, and show that the help of these two options can also lead to improvements in the performance of the models. Variance regularization is also a successful self-supervised learning method, which is related to the concept of total coding rate, which is part of the method proposed in this article. Going beyond achieving a good self-supervised performance, this algorithm additionally shows a strong clustering performance, and directly also learns a meaningful semantic space for the latent representations. One other thing that they mentioned is that the concept of population consistency, shown in this reference, is closely related to the constraint functional that they have discussed in this article. The use of data augmentation in this work is to ensure the correct clustering of the training data, and they mentioned that their findings are also consistent with the literature. Going to the problem setup, in the input of this algorithm, we have a union of nonlinear and low-dimensional manifolds, x1, x2, all the way till xn, assuming that all of them are homomorphic to RDI for some DI. And the data points xi, which are d-dimensional data points, are sampled from a union of these manifolds. Now the objective here, the first objective is clustering, meaning that you want to assign each data point to a manifold. You also want to parameterize and represent these different manifolds. So the proposed method is going to essentially act as a function f that takes a data point and returns the cluster and a representation z, which z belongs to an embedding space. The ideal goal is that eventually the assigned clusters be a permutation of the actual ground truth clusters. Also, z is supposed to be the coordinates of the manifold xc, c being the cluster index that is assigned to the data point x. An additional constraint that, if enforced, can help making the representations easier to work with is perpendicularity. To define this, basically take two of these manifolds that are different, meaning that j is not equal to k. Now, if we take zj, the set of the embedding z's of all of the data points that are in xj, and correspondingly, if we define zk this way, we want to have this orthogonality. And the definition of this orthogonality is this. Here is a critical component of this article that motivates the use of data augmentation as a central part and as a major enforcer of geometric constraints. The argument is that to make clustering possible with a neural network, additional geometric constraints are required. An example of this is figure 1. So neural networks provide a large capacity to be utilized in representing manifolds. Now we can see on the left where there was no additional geometric constraints enforced, the network has learned these two arbitrary clusters. However, the use of Gaussian noise as a simple data augmentation technique in here allows the network to be utilized in a sense to output these two nicely clustered manifolds. We can also see that this orthogonality is manifested in the semantic space of representing these manifolds. Note that this picture is related also to this part, where the article explains that clustering always involves implicit assumptions. Again, if a neural network is trained on example data, such as the one we saw above, to learn a cluster assignment function, the resulting clustering will be arbitrary and will not resemble any sort of additional geometric constraint that is not clearly identifiable. They again mention in order to utilize neural networks for this purpose, one needs to introduce constraints explicitly. The idea in what we saw in figure 1 is that to be able to separate the two spirals from each other, we just need to ensure that all close neighbors of a point from a data distribution are assigned to the same cluster. So it's the same as the idea of local neighborhood, which is taken care of usually by augmentation, meaning that small perturbations in the data space should not lead to major perturbations in the semantic space. So for a specific data distribution, they come up with this df here, which is basically a constraint functional. The major property to consider for it is that all cluster assignment functions f that makes d, this constraint functional, attain its minimum value, assuming that that minimum value is 0, and also cluster data points to the ground truth number of clusters, will correctly cluster all the data points. An example definition of it is that we can construct a functional that takes value 0 for all clusterings that satisfy the locality constraint and above 0 otherwise. Here's another definition of D that basically leads to the linear subspace clustering definition. In practice, we cannot necessarily make it 0. A more practical way that is shown in this article is to use an additional weighing parameter here and then define this loss this way, which includes the defined constraint as well. So in the definition above, the clustering loss is basically the loss that enforces the function f to cluster the dataset, and then you have a suitable hyperparameter lambda, and use this no loss to learn the model. So we talked about the first component of the manifold clustering and embedding. The second was the learning algorithm, which basically takes care of the manifold learning component. In this work, maximum coding rate reduction, which was introduced in this article, has been used. Consider that X is the dataset, meaning that it's the union of all the manifolds from 1 to n. The distribution for each manifold xj is written as this way. And if you have a certain encoder, you would have that encoder represented as f, which takes this distribution and maps it to the distribution in the semantic space. Note that this doesn't output clustering output at this point. So you have z's of this space. Now to define the Gaussian coding rate function this way, so if you have this representation z and this, note that covariance of z is essentially the average over this distribution. They mentioned that this also is approximately the Shannon coding rate of a multivariate Gaussian distribution given the average distortion epsilon. As the next step, let's assume that the cluster assignment function c is given, which taking a data point x is going to output something like I, which is going to be the index of the manifold that you're assigning x to, meaning that the index of the manifold that it says x belongs to. Having this, now we can use the average coding rate in this particular cluster I in which the definition of z is essentially f applied on the distribution of the manifold I. Now, according to the maximum coding rate reduction principle, the thing that we need to optimize is this. The optimization of this is in the direction of maximization of the entire component. This part is trying to make sure, in order to maximize the whole thing, you are minimizing this part, therefore pushing the manifolds into lower representations, while at the same time that you're enforcing this low dimensional representation for each one of these individuals, you're trying to maximize the union of all clusters, and this helps also in avoiding the collapse of representations. It has also been shown that the maximum coding rate reduction also maintains and guarantees the perpendicularity requirement, meaning that for two unequal manifolds, it maintains that zi is perpendicular to zj, and the rank of each one of these zi's is as large as possible. Now here is where the neural manifold clustering and embedding loss function comes into the article. The idea is that you want to extend the definition of maximum coding rate reduction to the case where the labeling function cx is not there. And basically the idea of this paper is to jointly learn this in a multi-stage training pipeline and also optimize the MCR2 objective. Thus, they define the loss of NMCE this way. So given an epsilon and an encoding function f, you have this. Now the part that has to do with data augmentation is this. Assume that tau and tau prime are two random transformations. So you take data point x and you have two representations this way. Now you give them to the encoding function and you get two pairs of cluster in this and z, basically performing the clustering and embedding. Now there are two things that the augmentation is trying to help us to achieve. One is that we want the two transformations of a single point to be mapped to the same cluster. This can be enforced by essentially using the average of C and C prime to perform the clustering assignment. And the second objective is that the learned feature embeddings, Z's, of these augmented data points, they have to be similar if if they both descend from the same point, in this case, being X. This constraint is defined this way. This is the second one. So D of F, or constraint of F, is that you want this to be there. It could be, for example, things based on cosine similarity or L2 distance. Now they mentioned that trying to optimize this from scratch is going to be kind of impractical, which requires the existence of a multi-stage training. Again, the motivation is that it is difficult to optimize the full NMC objective from scratch, and this from scratch is the key part here. So it's something, for example, like similar, let's say, to what we had in Suave, paper by Facebook, noting that if the proper operation of a part of the objective depends on basically a good performance being already achieved by another component, this kind of situation might motivate a multi-stage training. They mentioned that to achieve high coding rate difference, the objective, it is critical to achieve high total coding rate first, so we resort to multi-stage training procedure. And they define and use this new objective called total coding rate, which is like this. And they mentioned that this by itself is a novel self-supervised learning objective. And they show that this objective encourages the covariance of Z to be diagonal, with the similarity constraint basically behaving similar to VIC-REG, another famous self-supervised learning scheme. In here they have provided the details of their experiments, mainly the architectural configurations. They have provided comparisons with many of the important works in this domain. One important thing to note about their synthetic experiments is this part where they say, we perform synthetic experiment by clustering a mixture of manifold structured data, and this is how they have generated it, by passing Gaussian noise through two randomly initialized MLPs. Here they also have the details of the experiments they have set for self-supervised learning and clustering of natural images. As for the training strategy, or like their multi-stage training strategy, here are the key stages of this training. So first, you train with the total coding rate objective. In the second stage, you reinitialize the last linear projection layer and add a cluster assignment layer. Then freeze the parameters in the backbone network and train with two new layers with the full neural manifold coding and embedding objective. And third, fine-tune the entire network with the NMC objective. They find that averaging features obtained from images processed by the training augmentation improves the result. So they also create these 16 average experiments, which are basically 16 augmentations used per image. Now going back to the table here, look at this part. Now they mention here is that, as it is shown in the table, without augmentation, SVM using the projector head gives the best accuracy, which is surprising, particularly because in the self-supervised learning techniques, mostly pool features are being used. Now, when averaging is used, SVM with pool feature becomes the best performer. They have conducted more experiments, mainly the case in which limited label data are available, and they've shown that the project features is going to be essentially outperforming the pool features, leading to believe that the total coding rate objective encourages learning of meaningful feature in the latent space. And the question, how is it different from before, and how does it mean that the latent space learned here is more meaningful and more interpretable, is that the gap between the performance of pool and project features is often large in the previous works. Here they have the result of the clustering performance. They have utilized the three metrics of clustering accuracy, normalized mutual information, and adjusted random score, or ARI. The interpretation of the results is this part, that this method is outperforming the results of the previous methods. To sum it all up, this paper proposed a general method for manifold clustering and embedding. This was done by addition of geometric constraints to make these clusters identifiable, and then performing clustering and subspace feature learning using NMC objective. which had the MCR2 objective as its main component. The relationship between that and self-supervised learning was discussed, and the competitive performance was demonstrated. Also, this is a key reference for this work, which is the work that basically introduces the maximal coding rate reduction.